Welcome to the Deep Dive. Today, we're plunging headfirst into something really transformative happening in tech right now. This quiet revolution in robotics.
It really is picking up steam.
Yeah, so our mission here is to unpack the cutting-edge advancements, the things that are moving robots from, those very controlled factory floors.
Right, the cages.
Exactly, into the messy, unpredictable real world doing complex stuff.
And, at the heart of that shift, it's really about these powerful new AI models. Specifically, vision language action models. They're game changers.
Okay, vision language action models, we'll definitely dig into that. So this deep dive is basically your shortcut to understanding why now seems to be the moment for robotics. We've gone through the sources you shared, pulled out the key insights. Hopefully you'll leave feeling informed, maybe even a bit amazed.
Let's jump in.
So historically, when we think robots, it's often those superstructured places, power plants, warehouses.
Doing the same thing over and over.
Very repetitive motion, exactly. Hugely impactful, no doubt, but limited in scope.
Definitely.
And we've all seen attempts, maybe videos online, trying to get robots into, let's say, semi-structured places, or just the real world. I remember that well-known video of a humanoid
Oh, yeah?
kind of struggling with a task that seemed, well, pretty simple on the surface.
It really highlighted the difficulty, didn't it? Moving beyond that perfect predictability.
Absolutely.
And look, today we see impressive things like humanoids dancing. That shows really complex physical control, which is great.
Right, the agility is there.
But the real breakthrough, I think, is enabling robots to deal with those semi-structured objects, things that aren't perfectly placed, things like, well, like clothes.
Yes, that example from the source material is fantastic.
Yeah.
A robot dealing with clothes just out of a dryer.
Think about that pile.
Exactly. It's inherently chaotic.
Yeah.
You can't control the starting scene precisely.
Not at all.
Yet this robot, it picks out the shirts, puts them in a basket, and the full video even shows it taking them to a table and folding them.
That's a huge step beyond just picking up a perfectly positioned block.
So what really changed? What made that possible now?
Well, the obvious answer is the big AI wave happening everywhere. Robotics is definitely riding that wave.
Sure, general AI progress helps.
But specifically for these kinds of tasks, it's the work in vision language action models, or VLAs. That's the core innovation here.
Okay, VLAs. Let's unpack that. Maybe start with the foundation. Vision language models, VLMs.
Right. So VLMs, or multimodal LLMs, are probably familiar to many listeners. You give them text and images, maybe in a prompt.
Like asking a question about a picture.
Exactly. That input goes into a transformer model, this powerful AI architecture, which then sort of auto-regressively generates an answer, usually in text. It understands the image in relation to the text.
Makes sense. We use models like that all the time now.
So a vision language action model, a VLA, is essentially taking that VLM concept and adapting it specifically for robots.
Okay. So the action part is key. It's not just understanding, it's doing.
Precisely. Instead of just answering questions about what it sees, a VLA also gets input about the robot's state, like, where its joints are positioned.
Its physical self in the world.
Yes. And then critically, it's asked to produce actions, commands to actually control the robot directly.
Okay, that sounds like a significant leap. But if they're built on similar VLM principles, what are the big hurdles? What makes training a VLA so much harder than a VLM? It can't just be plug and play, right?
No, definitely not. And that's a great question because it gets to the core challenge. See, for VLMs, you can get tons of data from the web, billions of images, text descriptions.
Right, the internet is a huge data set.
And you can often use existing powerful models and just fine-tune them. The pipeline for training VLMs at scale is, well, pretty established now.
But for VLAs?
For VLAs,
Yeah.
especially if you want that really complex, dexterous, frontier-level behavior, it's an open question where you get that kind of data from. What's the web equivalent for robot actions?
Good point.
The source material quotes someone saying, this is basically the trillion-dollar question for the industry. How do you get enough good robot data?
So data is the big one. Are there other challenges too?
Oh, yeah. Adapting the VLM architecture itself for what's called high-frequency control. Robots need incredibly fast, smooth, continuous commands to interact with the world properly.
Not just slow, jerky movements.
Exactly. Millisecond-level adjustments. And then there's deployment. There's no standard way yet to get these huge, complex robot policies running reliably in lots of different places, on the robot itself or on local servers.
Okay, massive challenges. So how does a company like PI physical intelligence tackle this? You mentioned they built their data engine from scratch.
That's right. Their whole approach seems built around creating a scalable data pipeline. First, they pick a set of challenging tasks, folding clothes, bagging groceries, and they keep adding more.
Pushing the boundaries.
Then, they use human operators with a custom teleoperation system. They mention these leader arms.
Leader arms, like puppeteering.
Kind of, yeah. The operator physically moves these arms, tracing out the motions they want the robot to do.
Oh.
And software translates that directly to the actual robot's movements in real time. This lets them demonstrate and record data for really complex, fiddly tasks.
So they're capturing expert human demonstration data.
Exactly. Collecting it constantly, annotating it, and feeding it into their training process. And the result is models, policies that can actually do those tasks autonomously, like the PI0 model folding shirts we talked about.
And the scale they achieve seems critical. You mentioned the Open Cross embodiment beta set was around 3,800 hours.
Yeah, mostly static scenes. A good starting point, but limited.
But PI, after just 6 months with their pipeline, hit 10,000 hours of successful episodes.
That's right. Across tens of environments, hundreds of tasks. A huge leap in volume and variety.
And then another 6 months later, even more static data, but crucially, also data from mobile robots moving around.
Yes. Mobile manipulation setups. That massively boosts the diversity. Hundreds of different scenes, different environments.
That scale and, importantly, that diversity must be what unlocks the next level of capability.
Absolutely. This scale and diversity enable new leaps. It's fascinating.
It feels like there's an analogy here to how VLMs themselves developed.
There really is. If you look at the VLM world over the last, say, 3 years, we went from pretty basic conversational agents to these incredibly sophisticated multimodal reasoning models, coding assistants.
Right, the progress was rapid.
VLAs seem to be on a similar track, just maybe lagging a bit time-wise.
So what did that timeline look like for VLAs?
Well, early 2023, we saw the first ones, like Google's RT2. They showed glimpses of generalization, but were held back by the lack of data we just discussed.
Okay, the data bottleneck again.
Then, towards the end of 2024, we started seeing the first really dexterous multi-root VLAs.
Multi-root meaning?
Models that can coordinate multiple parts of a robot, like both arms, or a whole humanoid body working together. Think Google's Gemini for robotics and NVIDIA's models.
And PI0 fits in here.
Yeah, PI0 is highlighted as maybe the most dexterous multi-root model from that period, and importantly, it's open source. A lot of these models also adjusted their architecture to output actions using diffusion.
Diffusion, like an image generator.
Similar underlying tech, yeah. But here, it helps generate those really smooth, high-frequency control signals robots need for fluid movement.
Okay, interesting. So that brings us to PI's next big step, PI05. You mentioned it has open world generalization. That sounds huge.
It is potentially a very big deal. PI05 achieves this, first, by training on an even more massive and diverse data set. Static robot data, mobile robot data, but also lots of general VLM-style data from the web, object detection data, language annotations.
So broadening the knowledge base way beyond just robot actions.
Exactly, and they use a specific architecture. A big pre-trained transformer, like a standard powerful AI, but expanded with a special action expert transformer.
Action expert.
Yeah. So the model is trained to do two things: answer general questions about the scene, just like a VLM, and break down high-level human requests like clean my bedroom into smaller steps.
Okay, task decomposition.
Right. And then that dedicated action expert transformer handles generating the precise, continuous actions needed to actually do those steps.
And this allows PI05 to do these really long, complex tasks, up to 10 minutes. In places it's never seen before.
That's what they're showing. It seems to be one of the first really strong signals that broad generalization, the ability to work reliably in totally new situations, is emerging in robotics.
The example sounded incredible. Chelsea asking it to clean up in a new kitchen, or Laura just saying, clean the bedroom, and the robot figures out, throw trash away, make the bed, and just does it, controlling itself for minutes.
Yeah, the policy is running autonomously for extended periods, handling multiple subtasks. It's pretty remarkable to watch.
How did they test this generalization capability rigorously?
They did something quite clever. They trained PI05 using data from a varying number of different homes, but always kept one specific home location, completely separate, held out.
Okay, a truly unseen test environment.
Right. And they found that as they added training data from more and more different homes, the robot's performance in the completely new held-out home generally got better and better.
That makes intuitive sense. More variety helps generalization.
But here's the kicker. Eventually, the performance in the unseen home actually matched and maybe even slightly beat the performance achieved when they specifically trained the robot using data from that held-out home.
Wow. So training on broad diversity was ultimately better than training just for that specific environment.
Exactly. It really demonstrates that adding more diverse training data from different homes directly boosts the model's ability to handle completely new environments effectively.
That's a powerful finding, which leads to an interesting point about bottlenecks.
Yeah.
You might assume the hardware, the robot bodies, is the main limitation.
Oh. Right. That's a common assumption. But what's fascinating is PI's research suggests that might not be the case anymore. They believe one of the main bottlenecks now is actually software and, well, just the intelligence of the AI models.
Software and smarts, not metal and motors.
Increasingly, yeah. And they have this really compelling piece of evidence in the source material.
Oh, what's that?
Their model, PI-05, presumably, successfully controlled a robot they had never physically seen, never had access to. It was located, like, really far away.
Right.
And it performed a full end-to-end task, making a cup of coffee.
On hardware they'd never touched.
Exactly. And the key thing they stress is they didn't need tons of tweaking and iteration to make it work. They got the video relatively quickly.
That strongly suggests the model itself is adaptable, that it can generalize across different physical robot platforms without needing huge amounts of specific re-engineering.
Precisely. It supports this idea that the software, the core policy, can potentially run on lots of different hardware without them needing massive upfront investment for each new robot type.
That seems very significant for deployment.
It really is. And it fits with their open approach, too. They mentioned working with other companies, even like literally sending them the model checkpoint, the trained AI brain for them to run inference with.
Just handing over the model.
Yeah, it points to a focus on collaboration and maybe tackling the software challenge together, because the problems are still huge.
So if the biggest bottleneck is shifting towards software and model intelligence, what's the ultimate bottleneck holding back even faster progress right now?
Well, according to the source, PI believes the biggest constraint now is actually talent, attracting the very best researchers, engineers, and operations people in the world to work on these incredibly hard problems.
Finding the right people.
Yeah, they emphasize that the scientific problems, the engineering challenges, the operational hurdles, they are far from solved. It's a research-heavy field, and they're actively trying to hire the best minds to accelerate things.
Wow. Okay, so this deep dive has really painted a picture of how these vision language action models are the engine driving robots out of constrained spaces.
Into adaptable real-world scenarios.
And it's all fueled by these massive, diverse data sets and sophisticated AI architectures like PI-05.
And that shift really highlights how crucial software and model intelligence are becoming, perhaps even more so than the hardware itself in some ways, enabling deployment across different platforms much faster.
It's a fundamental shift in perspective. So let's leave our listeners with this. Considering these breakthroughs in open world generalization and this ability for one core AI model to potentially control lots of different robots, what kind of totally new services or maybe personal robotic assistants might actually become reality soon in our homes or maybe in industries we haven't even thought of yet, doing things we can't quite imagine today?